Hello everyone, my name is Sunit. I'm third year PhD student and my advisor name is Professor Kishan Rotherberg. So today I'm going to present my work, Interpacket Gap as a novel metric for heavy hitter detection with programmable switches. So what are heavy hitters? The flow in network traffic stream that contribute most of the traffic in the fixed measured time interval are called heavy hitters or elephant flows. For example, in this figure, a flow table is maintained which is used to count the number of packets for each flow. Here I use the three different colors to indicate the flow ID. So when a packet enters to the switch, switch extract the flow ID of each incoming packet based on the 5 tuple. And based on the flow ID, the corresponding counters is increased by 1. So at the end of each measuring time interval, controller read the register instances to extract the counter values of each flow and decide the flow is heavy hitter or not. And then controller reset all the register instances to 0 and start packet counting again for each flow. So heavy hitter is important for many network management applications, such as for network counting billing, congestion control, anomaly detection, quality of service, and traffic management. The most of the existing approaches are based on the counting packets or bytes. Several counting-based algorithms have been proposed and implemented on the programmable switches. We discuss the major problems which are not addressed in the most of the existing approaches. First is hidden heavy hitters. So generally we use fixed time interval to decide heavy hitter flows. In this case, we can miss some of the flows which are heavy hitters between the two consecutive intervals, but those flows are not recognized by each individual time interval. Second problem is reporting time. We should report the heavy hitter flows as soon as possible, but in the existing approach, we have to wait till the end of each time interval, which is not acceptable for DOS attack or traffic engineering application. And the third problem is high switch memory overhead. It is possible to reset all register instances at the same time, which can create inconsistency. For solution, we have to maintain two tables within the programmable switches. As shown in the figure, first table is active to count the packets and the controller reset the second table. In this next time interval, second table is used for counting packets and other is reset. However, maintaining two tables within the switch hardware is not an efficient approach because of the limited resources in hardware switches. So for solution, sliding window based approach is capable to solve these problems. However, it is hard to implement on programmable hardware. And also this approach consumed high memory. We propose a novel metric interpacket gap for heavy hitter detection. The major benefit of using interpacket gap are we don't need to rethink the existing data plane algorithms completely. The proposed approach can be implemented on the programmable switch hardware, and we don't need to maintain two tables which save memory of switch hardware. So our main idea is illustrated here. There are two tables. In the first table, we maintain counters for each flow and decide the heavy hitters based on the large counter values. While in the second table, we calculate interpacket gap for each flow and lower IPG value represent the heavy hitters. The given figure is showing that the difference in maintaining the flow state. For counter-based approach, we use flow ID and counters, while in our proposed approach, we maintain flow ID, exponential moving average, and last time stamp. For exponential moving average, we use the standard formula as given here. So for validation, we perform some tests using QAIDA ISP traces. We consider top 2000 flows for testing. In this figure, first y-axis represent the total number of packets of each flow in the fixed time intervals, and second y-axis denotes the weighted interpacket gap at the end of time interval. The figure confirms that IPG metric is suitable for heavy heater detection. In the next slide, however, there are two problems or limitation in the proposed approach. Since exponential moving average focus on the recent changes, we are limited to measure heavy heaters for a small time interval. Another problem is mice flows can also have lower IPG. In that case, it will be difficult to differentiate between the heavy heater and non-heavy heater. So for solution, we introduce another metric called tau. We update this metric based on the flow state. In the first figure, there are two states, non-heavy heater and heavy heater. Here states are represented by interpacket gap. So we check the flow state in every time interval. If the current flow state is below the predefined interpacket gap threshold, for non-heavy heater, tau metric is decreased by N2. Otherwise, it will increase by N1. And the second figure is showing more complex scenario where we can consider different number of states. For better understanding, here is an example. There are three flows. At the end of each time interval, we compare the current weighted IPG value with predefined IPG and update the tau metric accordingly. So as we can see that the tau metric for blue flow is increased for each time interval because of the low interpacket gap as compared to the other two flows. And when the switch find tau value above the predefined threshold for any of the flow, switch will report that flow as a heavy heater. Our algorithm is given here. So first packet enters to the switch and flow ID and ingress timestamps are calculated. In the fourth step, switch checks that the flow IDs exist in the table, in the flow table or not. If flow ID does not exist, switch looks for free space in the flow table and based on that flow table is updated. On the other hand, if the flow ID exists in the flow table, we calculate the current interpacket gap and weighted IPG. In step 6, for every wrap timestamp, we update the tau metric and compare with the predefined tau threshold and report the flow to the controller accordingly. So for evaluation, we use barefoot Tofino switch ASIC and used OSNT and TRX as a traffic generator. For dataset, we use Qaida 2016 ISP traces and perform tests using 3 different measuring time intervals. We use heavy keeper algorithm, which is based on the counter, and we modified the heavy keeper algorithm based on our proposed design. So here HK count represent the heavy keeper based on counter, and HK IPG indicates the heavy keeper based on interpacket gap. We use 32 bits for flow ID, 16 bits for weighted IPG, and 16 bits for timestamp, and 8 bits for tau metric. For performance evaluation, we use F1 score, precision, and recall metric. Here x-axis represent the memory uses in kilobyte. We observe that our proposed IPG-based heavy hitter detection solution can detect heavy hitter with around 0.90 precision and 0.95 recall with only 144 kilobyte memory. We analyze the performance for different measuring time intervals and find that the precision and recall are consistent for large memory sizes. We also evaluated the detection time of heavy hitters by our proposed approach. As shown in the figure, we are able to report the flows as soon as possible when they turn into the heavy hitters. On the other hand, for fixed time windows, we have to wait till the end of time interval. In the next slide, we analyze how our proposed algorithm impact on the throughput and latency, and also discuss about the resource consumption. So first we measure the throughput and latency without any algorithm. Just output packets forwarding without applying any actions. In the second case, we measured the performance with our algorithms. So as we can observe in figure, the throughput is not affected in both the cases, as expected from a line speed hardware pipeline. The difference in the latency with and without the proposed algorithm is around 176 nanoseconds. The P4 pipeline complexity of the proposed algorithm does not affect much on the overall performance. And the table shows that resource consumption of our algorithm implementation in the P4 Tofino switch. We can see that the resources use less than 10% except for the meter ALU and hash distribution unit. In conclusion, we proposed a completely different approach to detect the heavy hitters using the interpacket gap. Our method is windowless and support push-based approach where switch reports the controller at the same time when the flow turn into the heavy hitters. We implemented our proposed algorithm on Tofino switch and evaluated using the real Qaeda traces and achieved high accuracy. Thank you so much.